We're going to be looking at some more series tests to determine whether they converge or diverge. So we're looking at the divergence test, the p-series test, and the integral test in this section. So let's go ahead and start with the divergence test. The divergence test is just as it says. It only tests for divergence. It can't give you any other information. Now this is also known as the nth term test for divergence, because we're basically talking about what's happening at the nth term as n approaches infinity. So this is the divergence test. So quick note, the only two conclusions here are diverge or inconclusive. Now I cannot get converge from this. If it's diverge or inconclusive, if it's inconclusive, that means I have to try another test. It can still diverge, but this test is not picking up the fact that it could diverge. Okay, so it's either diverge or inconclusive. Those are the options. Well, basically the divergence test says if we have the limit as k approaches infinity of some sequence, and I get that limit not equal to 0, so it could be infinity, it could be 2, it could be negative 12, it just cannot be equal to 0, then the series based on that sequence diverges. So then the series a sub k diverges. That's the only outcome here. If it does equal 0, then it's inconclusive. Okay? It doesn't mean converge, it means inconclusive. So that's a divergence test. We'll look at some examples here after we put out all three of these different tests that we're going to be looking at. The p-series test is a nice little test. It's really easy to use. It just has to fit a particular form. So when we're talking about fitting a particular form, it has to be the sum from k equal 1 to infinity, and of course that could be a different variable as well. And the p-series test looks like 1 over k to the p. So k is the term that's changing from 1, 2, 3 up to infinity, and then p is some number. So the rules here for the p-series test is it will converge under certain conditions. It will converge for p greater than 1, and of course it would diverge otherwise. So it will diverge for p less than or equal to 1. Now there's a special case of the p-series test. That's k equal 1 to infinity of 1 over k, just 1 over k. The implied exponent is a 1 here, and so it obviously diverges, but this is called a harmonic p-series, and specifically it's called a divergent harmonic p-series. And we use this a lot when we're using some of the comparison tests that will be coming up in some other sections. So it's a divergent harmonic p-series. So it's just a special case of the p-series. Okay, so that's the nth term test for divergence. It's also the p-series, and then now let's look at the integral test. Now the integral test basically is assuming that you can integrate anything using any techniques from Calc 1 or from Calc 2. So all of those different integral techniques are still in play. So the integral test basically looks at the integral of the sequence. So the way that we'll write this out, we'll say suppose, the s with the p is called suppose. F is a continuous positive. And these are all important. I have to check for all three of these things. F is a continuous positive decreasing function for x greater than or equal to 1, and we need to let a sub k, the sequence, be replaced with our function notation f of k. And this we will do for k equal 1, 2, 3, etc. Then what happens then, and this makes sense because summation, using our summation sign here for integers, makes sense that we would rewrite that in terms of the summation for integrals. So I just replace that then. Now, the options that can occur, the outcomes that can occur here, are either both the sum and the integral converge, or they both diverge. So both the sum and the series, or in the integral, converge, or both diverge. That's the outcome here. So if I can make some conclusion about the integral, that's telling me the same information that I need for the summation or the series. If they converge, basically that means when I evaluated the integral, is not equal to the value of the series though. So we can't draw that conclusion. So these are the two tests. They're on your formula sheet. So when we're looking at these two tests, or these three tests, sorry, I need to be able to look at a particular series that's being given to me, and then I need to figure out what test to use. So the way I usually, my strategy is I always start with the nth term test for divergence. It's an easy one to use. And if it diverges, I'm done. If it doesn't diverge, then I need to try the other tests. So that's usually my strategy. But let's go ahead and just start looking at a whole list of problems that you'll see in your homework set. And then from there, what we can do is start talking about strategies for which test to use and when. So this first one, let's go ahead and look at this series, k over 5k plus 1. And what we have here is they're telling us to use the divergence test. So the divergence test, first of all, on your homework assignments and on your exam, you always need to name the test you're using. So I'm going to call this the divergence test, so I'll always write out what that is, and you should be doing that on your work as well. So for the divergence test, what we do is we take the limit as what we're going to do here then is think of this as, again, a series, or if I want to think about this as a k approaches infinity of the sequence producing part of the series, I take my limit and I would get 1/5 here. But I have to have a reason why, because the degree in the numerator equals the degree in the denominator. So the limit is the ratio of the leading coefficients. So it's really super important here that you first of all name the test. If you take a limit, you have to explain how you got your answer. In this term, I use shortcuts. So the thing here is that 1/5 does not equal 0, and by the divergence test, this implies that the series diverges. So that's the setup. Name the test, find the limit, explain how you found your limit, use this type of reasoning, and then draw your conclusion. And you have to be really careful that you meet all of those criteria for partial credit on exams, or for even credit on exams. Next one, they give us the divergence test as well as a hint. So it's nice we're starting off with some of these problems where they're telling us which test to use. So the divergence test, again, you have to name the test, and then you need to show your work on the criteria for the test. So that would be the limit as k approaches infinity of 5 over 1100 plus 2k. That's equal to 0. Why is that limit equal to 0? Because the degree in the numerator is less than the degree in the denominator. Well, if that equals 0, that would imply then that the divergence test is inconclusive. So therefore, the divergence test is inconclusive. Now this particular problem is not asking me to go any further than that. It's just saying use the divergence test and figure out diverge or inconclusive. Those are the options there. But if I had to keep going and try and figure out what's going on here, I could use the integral test, because this would integrate into a 1 over u du, and then I could evaluate it from there. But this problem is not asking us to go that far. This next problem is also telling us that they want us to try using the divergence test right here. And the only two options are, I can say that it diverges or it's inconclusive. Now for this test, if it's inconclusive, technically I should keep going to figure out what's going on, but the question isn't asking us to do that. So first of all, I name our test. I note the criteria of the test is to take the limit as k approaches infinity of 2k cubed all over k factorial. Now, taking this limit isn't as obvious as you might think because I can't really compare the power in the numerator and the denominator very easily. So let's think about it like this. If this was 2k cubed and this is k factorial, that would be k minus 1, k minus 2, k minus 3, all the way down to 3 times 2 times 1. So as long as k was higher than 3, we should be good to go here, because then that would be k equal 1, k equal 2, k equal 3, then the power would be higher in the denominator. So I'm going to say that this is going to go to 0 because the degree in the numerator is less than the degree in the denominator. And that's values for k greater than or equal to 4, we'll say. Because at k cubed, if I had a 3 down here, then that would not even out. So that couldn't compare that. So I want to be able to look at for k greater than or equal to 4. So therefore, the divergence test is inconclusive. Okay, so as we keep working through these, we're going to start to see every problem is just slightly different. There's a little twist to each problem, so that's what you want to look out for. Our next problem, they're asking us to use the integral test, but before I can actually use the integral test, I have to show that all the conditions for the integral test are being met. So for the integral test, again, I name the test I'm using, and you have to make sure that this is on all of your work for your exams. I have to show, first of all, that it's continuous, it's positive, and it's decreasing. So these three things have to hold true before I can draw any conclusions for the integral test. So how do I show that this is continuous? Well, it's continuous because I'm starting at k equals 0. So if I start at k equals 0 and I put that into the denominator, I'm going to have square root of 7, square root of 8, square root of 9, etc. So there's no time that I'm ever looking at the square root of a negative number or where the denominator equals 0 and it's undefined. So it's continuous, yes, because k cannot equal negative 7 basically would cause the problem. It is positive because I have a positive in the numerator and I have a positive square root in the denominator. And then how would I show that it's decreasing? Let's talk about that. There's several ways we can do that. I will show you a couple ways, and then based on the problem we're looking at, one way might be a little bit easier than the other. So for decreasing, one thing I could look at is I have a fixed numerator. It's not changing, and the denominator is increasing and getting larger and larger. So what ends up happening is that fraction continues to get smaller and smaller as that denominator increases and the numerator is fixed. So that's one way that we could do that. Another way that we could do that is we could take the derivative of the function and we could show that the derivative is less than 0, or basically the derivative is negative. And in this case, the derivative is negative 3 k plus 7 to the negative 3/2. So that's definitely negative. So because it's continuous, positive, decreasing, I can go ahead and do the integral test now. Okay, so what is the integral test? That means I would integrate this from 0 to infinity, and I'm pulling those right off of the indices here, of 6 over, and then I, of course, change this to x plus 7 dx. So I'm going to rewrite this, the integral from 0 to infinity of 6 times x plus 7 to the negative 1/2 dx. So I'm going to use a u substitution on this. So again, all of the substitution techniques I've learned are applicable in this section as well. U is x plus 7, du would be dx. So this is perfect. So I'll have the integral from 0 to infinity. I'm going to pull this 6 out front, and then this becomes my u. So I have u to the negative 1/2, and then dx becomes my du. Now, I guess technically I should change my limits of integration. So these are in terms of x, and everything else is in terms of u now. So if x is 0, 0 plus 7 would be my u, and 7 would be my dx. new u, so that would be 7. And then infinity plus 7 is still infinity, so I'm good to go there. So let's go ahead and integrate that. I drag the 6 along, and I add 1 and divide by the sum. So when I add 1, I get u to the 1/2, and then I have divided by 1/2. When you divide by a fraction, you're actually multiplying by the reciprocal. So the reciprocal of 1/2 is 2 over 1, u to the 1/2. So this is 6 times 2 is 12, u to the 1/2, or 12 u, I guess I could write. I don't have to substitute back in for x because I already changed my limits of integration. And this is going to go from 7 to infinity. So when I plug in my upper limit, remember I'm actually taking a limit here. I have my 12 times the limit as u approaches infinity of the square root of u. So that's my upper, minus my lower, I plug in 7, square root of 7. So this particular limit, this is going to go toward infinity. So I have 12 times infinity, which is infinity. And then I have infinity minus 12 root 7, which is still infinity. So this means that the integral diverges. So that's the start of the conclusion that I can draw. Well, if you look back at the integral test, if the integral diverges, the series diverges as well. So this implies I should write the integral diverges. Therefore, the series diverges. Okay, so that's the integral test. The integral test you will not get any credit for if you don't show that these criteria are met, because these criteria are not met for all different types of series that we'll be looking at. Now in my math lab, let's run back up to the top of this problem. When we show that these are the criteria for the integral test, my math lab always mentions one more, but it's always assumed. So my math lab will also mention a criteria that you need to choose that basically says the function has a property that a of k is equal to f of k for k equal 1, 2, 3, etc. I guess this one starts at 0. So that's another criteria you'll have to make sure that you mark, but the 3 ones that I looked at are continuous, positive, and decreasing. So this one they're telling us to use the integral test as well. And because we're using the integral test, I need to show that that criteria of continuous, positive, decreasing have been met, along with that extra criteria that I can rewrite a sub k as f of k. So first of all, as usual, we need to name our test. So we name the integral test. And then I have to show that it's continuous, positive, and decreasing. So continuous, positive, decreasing. And again, that third criteria, or sorry, it could be the fourth criteria, I guess, would be a sub k is equal to f of k. Not much to show for that. So for continuous, I should be able to say, yes, this is continuous. And the reason it's continuous is the denominator does not equal 0 for any values of k that are possible. So if I had a negative 3/5, that would make the denominator 0 and I'd have a problem, but that's not an integer, and it's also not between 1 and infinity. It is positive because I have a positive over a positive, and this is how I expect you to show your work. And it's also decreasing, so I could look at this in two ways. I should say fixed over increasing makes the overall fraction decreasing. And of course the fourth criteria is met as well. I could take a derivative to show that too. So once I have shown that, the next thing I need to do is actually integrate this. So when I integrate this, this is going to be a u substitution, it looks like. So I'll look at the integral from 1 to infinity of 1 over the cubic root of 5x plus 3 dx. So I'll rewrite that as the integral of 1 to infinity of 5x plus 3 to the negative 1/3 dx. And then I'll use u substitution. So u is equal to 5x plus 3. Du then is 5 dx. So when I rewrite this, this would be u to the negative 1/3 du. But in order to get that, I needed to multiply by 5 on the inside and compensate with a 1/5 on the outside. So I'm going to drop my limits of integration on this one. Last time I just changed them, but this one I'll drop. So I'm going to drag along the 1/5, and then I'll have u to the 2/3 divided by 2/3. When I add 1, divide by the sum. When I divide by that fraction, I'll multiply by the reciprocal. So I end up with 3/10 u to the 2/3. But u is equal to 5x plus 3. Now I can plug in my limits of integration from 1 to infinity. So as I plug these in, I have 3/10 times the limit as x approaches infinity of 5x plus 3 to the 2/3. So that's my upper, minus my lower, 3/10 5 times 1 plus 3 to the 2/3. So this first term goes to infinity, and that ends up being what is helpful here. And then, of course, this is going to be minus 3/10 times 5 plus 3 is 8 to the 2/3. And I can actually take 8 to the 2/3 because, and I don't even really need to do this because my answer is infinity anyway, but since we can do it, we may as well. 8 to the 2/3 means the cubic root of 8, which is 2, and then 2 squared is 4. So I have infinity minus 12 over 10, which reduces to 6/5. So infinity minus 6/5 is equal to infinity. Therefore, the integral diverges, which implies the series diverges as well. And that's my conclusion. Okay, this one we're asked to use the integral test as well. That's nice when they give us the name of the test. It makes it a little bit easier to get started. So again, name the test that you're using. And you might say, well, they already told us the name of the test in the beginning, but that's not always going to be the case. Sometimes you're going to have to come up with your own test, and so it's always important to show that right away. So again, I need to show 3 things here, and I guess that 4th I'll include. Continuous, positive, and decreasing. And then, of course, that given almost at the bottom would be that a of k is equal to f of k. So is this continuous? And the answer would be yes, because the denominator does not equal 0, ever, from k equal 1 to infinity. Is it positive? Yes, because I have an exponent up here, this e to the 2k, that'll always be positive, and the denominator will always be positive, so the overall fraction is positive. And then is it decreasing? You could take a derivative to check, but what we have here is the numerator is constantly increasing, but the denominator, because it has a higher power, it's going to the 4k, is increasing faster. And so because the overall fraction is going to keep decreasing because the numerator is increasing but the denominator is increasing faster, it's going toward 0, it's decreasing. And of course the last criteria has been met as well. So now I have to integrate this. So to start to integrate it, I'd rewrite it, and I'm going from 1 to infinity, e to the 2k over 1 plus e to the 4k. And actually I'm going to rewrite these in terms of x. Now this is when you have to remember all of your integration techniques. Maybe pull out your formula sheet for integrals. But this is basically going to be a 1 plus u squared, or a squared plus u squared. So this is going to be an inverse trig when I get done. So let's go ahead and rewrite it so we can recognize some of those. I'm going to rewrite 1 as 1 squared, and I'm going to rewrite e to the 4x as e to the 2x squared. So what I have here then is I have an a squared plus u squared. So if I have a 1 over a squared plus u squared du, that's going to integrate into 1 over a inverse tangent of u over a. So that's what this is going to end up looking like eventually. We have a little bit more work to do here. But in order for this to work, a is equal to 1, u is equal to e to the 2x, du would then be 2e to the 2x dx. So I'd multiply by a 2 on the inside, compensate with a 1/2 on the outside. So I'd have 1/2 integral a squared plus u squared du. Now the du is right here, and that's up in this numerator. So that integrates into 1/2, because I'm pulling the 1/2 along, 1 over a inverse tangent of u over a. U is e to the 2x over a, which is 1. So rewriting, I have 1/2 inverse tangent of e to the 2x. And I'm evaluating this from 1 to infinity. So this is 1/2 limit as x approaches infinity of the inverse tangent of e to the 2x minus 1/2 inverse tangent of e to the 2 times 1. So 1/2. So now what does this bit do? Well, as x approaches infinity, this term right here approaches infinity. So this piece right here says what angle in the quadrant negative to pi over 2, or the interval negative to pi over 2, has a tangent that approaches infinity is the question. So as I'm looking at this, tangent's undefined at pi over 2, because that's sine, which is 1, over cosine, which is 0. So what I have here then is that angle is approaching pi over 2. It can't equal pi over 2 because I have parentheses here, but I have this angle that's approaching pi over 2. So I have my pi over 2 minus inverse tangent of e squared. So that is my answer for the integral, but this means, this implies that the integral converges, therefore the sum converges too. Okay, and so this is kind of the important conclusion, the sum is converging. I don't need a decimal approximation for this. I can just leave this as is. I just know it's not going toward infinity and diverging, so I know it has to be converging. But again, all of your integration techniques that you've learned up till now are fair game here, so make sure that you're keeping sharp on those. Next one, we're also using the integral test. So again, for the integral test, I need to start by showing a few things. So we'll name the test. Then I need to show 1, it's continuous. Second, it's positive. And third, it's decreasing, or the terms are getting smaller and smaller. And of course, that fourth one, I guess that we can mention is a of k is equal to f of k. So is this continuous? Yes, it is continuous, because if I rewrite this, this ends up rewriting as k over e to the 3k squared when I flip that, and the denominator here that I've just flipped over and found never equals 0. There's nothing I can plug in there to get 0 back out. Is it positive? Yes, because the numerator is positive, because I'm going from positive 1 to positive infinity, and the denominator is positive as well. And is it decreasing? Yes, you could take a derivative, or you could look at this and say, okay, the numerator is increasing, but the denominator is increasing even faster because I have e to the 3k squared instead of just a constant value of k. And of course that fourth criteria is met. So I should be able to go ahead and integrate this now and come to some sort of a conclusion. So I'm going from 1 to infinity, and I'm going to keep this as e to the negative 3x squared. I'm not going to flip that for integrating. So here what I'll do is I'll choose a u. So I'll have u equal negative 3x squared. du is a negative 6x dx. I have the x, but I don't have the negative 6. So I'm going to multiply by a negative 6 on the inside, compensate with a negative 1/6 on the outside. And here I'll go ahead and I'm going to change my limits of integration on this one. So for this one, if 1 is x, when I plug that into u equal negative 3x squared, I get negative 3 times 1 squared, which is negative 3. If I plug in infinity, this is going to be infinity squared times a negative 3, or yeah, infinity squared times a negative 3, so I'm going to get negative infinity. Now usually we go upper to lower, so I'm going to go ahead and rewrite this. So this will be e to the u du. So I'm going to rewrite this then as negative 1/6 integral. I'm going to flip this to negative infinity to negative 3, so lower to upper. But in the meantime, when I do that, what happens, I have to multiply by negative out front, so that becomes positive. So I have e to the u du. This one might have been easier just to leave alone and not change my limits of integration. The integral of e to the u is e to the u, and then I evaluate this from negative infinity to negative 3. So I'll have 1/6 e to the negative 3 for my upper, minus my lower would be 1/6 limit as u approaches negative infinity of e to the u. So as I approach negative infinity, this will equal e to the negative u. So that flips then into 1 over e to the u. And as u goes toward infinity then, that's going towards 0. So this whole term is going towards 0. And what I'm left with here is 1/6 e to the negative 3, which is 1 over 6e cubed as well. So what this means then is the integral converges. It's going toward a particular value. So I can get my stylus to work here. The integral converges. Let's see if I can get the stylus to go. So the integral converges, therefore the series converges. So that's our conclusion here. So being able to integrate all these different types of series is going to be very, very important. Now some of them you might not be as familiar with or maybe have forgotten, but make sure you run through your old integration techniques because they will be very important on this exam. So this one is another integral test. Now some of these have been converging and some have been diverging, so we have to make sure that we do all these checks. We can't just take some random guess at these. So again, we name the test. This will be the integral test. And with the integral test, I have to show continuous, positive, decreasing, and then that little a sub k equal f of k. That just means that I can rewrite the sequence in terms of an integral. So continuous, positive, and decreasing. Now one of the options is always that the criteria are not met and the integral test doesn't apply. So is this continuous? Yes, it is continuous because the denominator can never equal 0. It can never equal 0 because I'm starting with k equal 4 and I'm going up toward positive infinity. So k can't equal 0. And then the natural log of 1 would be 0, but 1's not in the domain. I'm starting at 4. So positive, yes. I have a positive over a positive. This is true because I'm working from 4 to infinity, so all my values are going to be positive in the denominator. And is it decreasing? Yes, because my numerator is fixed and my denominator is increasing without bound. So I should be able to integrate this now. And to get started, the first thing I need to do is to rewrite the integral as 6 over k, let's do x, natural log of x squared dx, and this is going from 4 to infinity. Okay, so this is a u substitution, so I'd let u equal natural log of x, and then du would be 1 over x dx. So let's go ahead and write that out. U is natural log of x, du is 1 over x dx. And I have all of that. I'm left over with the 6, so I'll have 6 out front. And then this 1 over x dx is my du. In the denominator, natural log of x is my u, so that would be u squared. And when I rewrite this, it'd be 6 integral u to the negative 2 du. So now what we can do, I guess I could change my limits of integration. I don't think I will on this one. I don't think I need to. Plus we're going to get natural log of 4 as one of my limits of integration. And so I'm going to go ahead and integrate, add 1, so I'd get negative 1 divided by negative 1. So this is a negative 6 over u. And then I'll evaluate that. Actually, I won't. I'll make a substitution. u is natural log of x. And now I'll evaluate it from 4 to infinity. So this is -6 natural log, -6 limit as x approaches infinity of 1 over natural log of x. So there's my upper minus my lower, which would be a -6 over natural log of 4. Okay, so -6. So natural log of infinity is going toward infinity. So the denominator is going toward infinity. The overall fraction then would be going toward 0 because 1 over a very, very large number is going towards 0. So this is -6 times 0 plus 6 over the natural log of 4. So what I get here then is 6 over natural log of 4, which means that it converges. So this implies that the integral converges. Therefore, the sum or the series converges as well. So a lot of these have been U substitutions. Make sure, again, you stay sharp on those integration techniques. So we've done quite a few integral tests and divergence tests. We haven't done any P-series tests. So let's go ahead and look at our P-series test. So, well, it says use an appropriate test, but this is a P-series. So why is it a P-series? Because it looks like 1 over k to the P. Now this k doesn't have to be a k, it could be an r, as long as the indice matches the base right here. So what this looks like then for us is the 5 is out front, and it doesn't matter if I'm multiplying by a constant. That doesn't affect whether it converges or diverges. So this would be 1 over k to the 3 halves. Okay, so 1 over k to the 3 halves. So this is a P series, so I name my series, or I name my test that I'm doing. And in this particular case, P is equal to 3 halves. Well, the criteria for the test, let me get out my sheet here. The criteria for the P series test is P greater than 1, the series converges. So that's what I have happening here, is the series converges because P is greater than 1. So the P series test is actually pretty easy if it's written out correctly. So the fact that I have a 5 here does not affect this. Another thing that won't affect this is if I am, I'm trying to think what other things. If you, let's say, subtract 5 and then square the bottom. So if it was k minus 5 quantity squared, or to the 3 halves. So hopefully we'll run into a few of those types of problems as well. And I guess before we go on to the next problem on this one, I probably should have looked at the divergence test first. If I took the limit of this, this would go to 0, so the divergence test would be inconclusive. But it's something I should always check, because if I can get it to diverge right away, it'll save me a lot of work. Okay, so for this one, they're not telling us what test to use. It just says use an appropriate test. So let's go ahead and go through our quick list here. I could use the divergence test, so let's go ahead and try that one to see if we can get an answer out of this. So for the divergence test, I go ahead and take the limit as x approaches infinity of x over x squared plus 6. And here I get 0 because the degree in the numerator is less than the degree in the denominator. Make sure you have the reason there. Therefore, the divergence test is inconclusive. So that means I have to try some other test. Okay, so let's kind of run down what we have here. I have a P-series test, so I have this one. It's not a P-series, so I can't use the P-series test because it's not over 1 over k to the P. And you might say, well, what? It's k squared though, but I have a numerator with a variable, so it doesn't fit that. And then I have the integral test, so I'm hoping that the integral test will work because that's really all I have to go by in it right now. So in order to use integral test, I need to show 3 things: continuous, positive, decreasing, and I guess there's that fourth I always don't think about too much. That's the a of k equals f of k. So I have continuous, I have positive, and I have decreasing. So let's go ahead and check these. Is this continuous? And the answer is yes, because the denominator does not equal 0. Is it positive? Yes, because I have a positive over a positive, so k is greater than or equal to 1. The denominator is always positive. The numerator could be negative if k was negative, but again, k starts at positive 1 and goes toward infinity. And then decreasing, the numerator is increasing, but the denominator is increasing even faster because the power is higher. And of course, that last one is met as well. So I should be able to go ahead and integrate this. So let's look at the integral from 1 to infinity of x over x squared plus 6. This is going to be a nice little u substitution. U is x squared plus 6. Du is 2x dx. So I'll multiply by 2 on the inside, compensate with the 1/2 on the outside, and I have the integral of 1 over u du. So this is going to be 1/2 natural log absolute value of u, and then when I plug in for u, I get x squared plus 6. And I'm going to go from 1 to infinity here. So my upper will be 1/2 limit as x approaches infinity of the natural log of x squared plus 6. That's my upper, minus my lower 1/2 natural log absolute value of 1 squared plus 6. So what ends up happening is this limit goes toward infinity. This x squared plus 6 goes toward infinity, and the behavior of the natural log graph, if you'll recall, was something like this. So as x is going toward infinity, the y value is going towards infinity as well. So I have infinity times 1/2, which is just going to be infinity. So I get infinity minus 1/2 natural log of 7, which is just equal to infinity, which implies the integral diverges. Therefore, the sum diverges too. Okay, so the logic that we follow here is we always try divergence test first, because if it diverges, it's really easy to take the limit. Get anything other than 0, you know it diverges and you're done. Try a p-series, if it is a p-series, and then keep going from there. This one they're just saying use an appropriate test as well. So let's go ahead and go through our list. Let's look at the divergence test. And we take a quick limit here as x approaches infinity. Of course, we are starting at 5, keep in mind, of 1 over x minus 4 to the 4th. Well, this is going towards 0. Why? Because the degree in the numerator is less than the degree in the denominator, so this would be inconclusive. But it's just a quick test I can usually do. So that's a divergence test. This is a p-series. Now remember, a p-series looks like 1 over k to the p, and this doesn't exactly match that, but it's pretty close. What I have here then is a k minus 4 to the p. So let's write this out. Now this is important that I'm starting at a 5 here, because if I was starting, let's say, at 3 or 2, etc., I would move up through 4 and this fraction would be undefined. So this is k minus 4 to the 4th. So this minus 4 does not affect whether this converges or diverges. So this is a p-series with p equal 4. And for a p-series, if p is greater than 1, make that look like a 4. P is greater than 1, that would mean that this converges. Now, as a quick note, integral test would also work to show convergence. Okay, so go through your list and usually go easiest test to the hardest test. So that way, if you can get an answer before you get to the more difficult tests, you save yourself a little bit of time. The next one also says use an appropriate test. So that means you get to decide which one to use. But again, I would always encourage you to start with the divergence test, because if it works, you're done very quick. So the divergence test basically takes the limit as x approaches infinity of 3x over e to the 2x. E to the 2x here. So here when I take the limit, I can see pretty quickly that this is going to go to 0, but it's not going to go to 0 because the degree in the numerator is less than the degree in the denominator. So this is going to be equal to infinity over infinity, which is an indeterminate L'Hopital's. So I end up using L'Hopital's rule here. So the limit as x approaches infinity, the derivative of 3x is 3. The derivative of e to the 2x is e to the 2x times the derivative of 2x, which is 2. Now, pretty clearly this equals 0 because the numerator is fixed and the denominator is increasing without bound. So this is inconclusive. Okay, second, this is not a p-series. So not a p-series, which would look like 1 over k to the p. And k would be what's changing here and e is fixed. So next I would look at the integral test. Now for the integral test I need to show my list of criteria first is met before I can actually integrate this. So my list of criteria are 1, continuous, 2nd, positive, 3rd, decreasing, and of course that 4th one then would be a of k is equal to f of k. Okay, so let me scroll back here a little bit so we can see our function. Okay, is this continuous? Yes, because the denominator cannot equal 0. Is it positive? Yes, because the numerator is positive and so is the denominator. Now the numerator could be negative if we didn't start at 1 and go toward infinity. If we had started at -5 and went toward infinity, it could have been negative, but it's positive over positive. Is it decreasing? Yes, because the numerator is increasing, but the denominator is increasing even faster, so the overall fraction is decreasing, and of course the 4th criteria is met. So I have to integrate this. So this is going to be the integral from 1 to infinity of 3x over e to the 2x dx. So the first thing I'm going to do is rewrite this. I'm going to pop that e to the 2x up top. I can't use a u substitution on this because I have a leftover x. So when I rewrite this, I'm going to have 3x e to the negative 2x. So I'm going to have to use some other technique of integration, and I think it's going to be integration by parts. So this is 3x e to the negative 2x dx. So integration by parts, I choose a u and a dv. I'm going to use my u to be 3x, du would then be 3dx. My dv is e to the negative 2x dx, and then if I integrate that, I'm going to get a negative 1/2 e to the negative 2x. So there's my setup. So again, I started with my u and my dv. And just as a quick review, the integration by parts is integral of u dv is equal to uv minus the integral of v du. Okay, so now let's go ahead and set this up and integrate it, and then I'll worry about evaluating it, but let's integrate first. So the integral is going to be equal to uv, so that's going to be minus 3x over 2 e to the negative 2x minus the integral of v du, so minus 1/2 e to the negative 2x times 3 dx. So I'm going to rewrite this quite a bit. So this is going to be minus 3/2 x e to the negative 2x, and then here I'll have a plus 1/2. Actually, it's going to be a plus 3/2. Let me pull that 3 out front as well. Integral e to the negative 2x dx. Now that I can integrate. So u is negative 2x, du is a negative 2 dx. In fact, I just integrated it up above when I did this integral right here. So I'm going to multiply by -2 on the inside, compensate with a -1/2 on the outside. And it looks like I will have -3/2 x e to the -2x minus 3/4 integral e to the u du. So minus 3/2 x e to the -2x minus 3/4. The integral of e to the u is e to the u. But in this case, I know what u is. It's -2x. So this is -3/2 x e to the -2x minus 3/4 e to the u. U is -2x. So I could probably simplify this quite a bit before I evaluate it, because remember, I'm going to be evaluating this from 1 to infinity. So we could find a common denominator, and I could also flip the e to the -2x's down. That would be an option. So I think I'll leave my fractions as is. So I'm going to leave this as -3x over 2e to the 2x minus 3 over 4e to the 2x, evaluated from 1 to infinity. So as I take my limit here, I can see the first term is going to go to 0, and so is the second when I evaluated infinity. But what I get here is going to be infinity over, or infinity minus infinity, which is actually an indeterminate form. So I guess I have to rewrite these in terms of a common denominator to write this as a single fraction. So to do that, I'm going to multiply top and bottom by 2. So I get minus 6x minus 3 all over 4e to the 2x. Now I'll evaluate this from 1 to infinity. So as I think about this limit as x approaches infinity of this expression, minus 6x minus 3 over 4e to the 2x. So that's my upper, minus my lower, minus 6 times 1 minus 3 all over 4e to the 2 times 1. So this piece right here, this is going toward infinity. The denominator is going toward infinity, but the denominator is going faster toward infinity because I have the x in the exponent. So this whole term is going towards 0. So I have 0 minus, here I have a -6 minus 3 all over 4e squared. So I have a minus, -6 minus 3 is a minus 9 over 4e squared. So this is 9 over 4e squared. Well, what this implies then is that the integral converges because I have a finite value here. Therefore, this series, or the sum that we're looking at here, converges as well. Okay, so that's my solution. So again, integration by parts. It's fun that that came up again. Okay, again, they're asking us to just use a test, use the appropriate test. There could be more than one test that would work. But I always think it's a good idea to start with the divergence test. Now for here to do the divergence test, we need to just take the limit as x approaches infinity of 12 over the cubic root of x, which of course is 0 because the degree in the numerator is less than the degree in the denominator, so it's inconclusive. So that means I have to try another test. So next one that I might want to try is the p-series test. And this is a p-series, so that's nice. This will be a quick solution here. So when I rewrite this, this would be 12 over k to the 1/3. Now the 12 doesn't end up mattering here. It's just a constant. It won't affect whether it converges or diverges. So basically what I want to do here is to say p equals 1/3. So that's my value that I want to compare. Now p is less than or equal to 1 in this case. Therefore, this will diverge. And you might say, well, wait a minute, the divergence test said inconclusive. Well, the divergence test basically checks and finds easy series that diverge. Some series could still diverge, but they don't find it using the divergence test. So the p-series test works great here, and I'm done. I could probably also integrate this, so we can note that as well. The integral test will work as well, but that's a lot more work. So if we can get the p-series test to work, that would be best. But there is more than one way we can do this. Okay, this next one again is the same instructions. They don't give us a test to use. So let's go ahead and start with the divergence test. Now this one is not going to be as obvious when we take the limit, so we might have to do a little bit of work here. So k, we'll do x approaches infinity. This would be the square root of 4x to the 5th plus 13 all over x to the 5th. Well, if we look at this, I'm trying to figure out what my limit is. I could rewrite this by separating the denominator, or sorry, separating the numerator. You can't separate the denominator. So this would be 4x to the 5th over x to the 5th plus 13 over x to the 5th, which is equal to the limit as x approaches infinity of the square root of 4 plus 13 over x to the 5th. Now I can't split this up into two square roots. I can't take this as root 4 plus root 13 over x to the 5th. So what ends up happening here is this term goes to 0 because the numerator is fixed, the denominator is increasing without bound, or you could say the degree in the numerator is less than the degree in the denominator, and I'm just left with the square root of 4 here. And of course the square root of 4 is 2. 2 does not equal 0. Therefore, it diverges by the divergence test. So here the divergence test worked for us to conclude divergence. Okay, our next one, again, they don't give us a test that we have to use, so we could go through our list. And I guess, you know what, we have another series test that we could use. None of these that we've looked at today so far, though, have met the criteria for that, but we better throw it back in the mix. So when we look at this, the divergence test is not going to be so obvious here. I don't think I'm going to get a conclusion from taking this limit. I'm not used to taking a limit where I have a base of a constant to a variable. I'm used to a variable to a constant. So that's not going to be as obvious. So the divergence test I don't think will work. This is not a p-series. I don't know how to integrate a to the u. I could go back and figure that out. But you know what this is? If I rewrite this, these are geometric series. So I could split this up into two separate geometric series. So 4 to the n over 7 to the n minus sum 1 over 7 to the n. Now as I rewrite these, this is going to equal 4/7, so I'm going to put a 1 out front, 4/7 to the n minus, I'm going to put a 1 out front, 1/7 to the n. Now the reason I put the 1 out front is then I can see what my value for a is if needed. So both of these are geometric series because I'm integrating, or sorry, I'm summing from 0 to infinity. So both are integrated series. So let's look at the first one. Let's look at our r value for the first one. So here r is equal to 4/7. Now the criteria for the geometric series is that if the absolute value of r is less than 1, which it is here, this converges. So for this next one, r is equal to 1/7, which is also less than 1, and it converges as well. So both of these converge. So therefore, the overall series converges too. Okay, so don't forget the geometric series. If you see something that looks like one, throw that in the mix as well. Okay, so it says use a convergence test of your choice. Well, a convergence test is trying to figure out whether this converges or diverges. Basically, they're saying figure out if this converges or diverges using the test of your choice. So as we work through this, we'd want to start with a divergence test. This is not a geometric series. It's not a P series. I could try and integrate it. I'm kind of thinking it might not integrate very easily. So I think the divergence test is going to be what is going to be helpful to me, I hope. And hopefully I can draw a conclusion from it. If I can't and it's inconclusive, then I'll have to figure out something else. So this would be 2x sine 2 over x. So this would be infinity times the sine of 0, because 2 over infinity is approaching 0. This would be infinity times 0, which is indeterminate. It's not an indeterminate L'Hopital's though, it's just indeterminate, and that means to do more work. Do more work. Okay, so the more work that I can do here is rewrite this. So I could get it in some sort of a L'Hopital's form. Now if I wanted to, I could pull that 2 out front, and I think I will for this case. Now this x I could rewrite as 1 over x in the denominator. So now when I take my limit, I'm going to get 2 from out front, from right here. And then the sine of 2 over infinity, that'd be the sine of 0, which is 0. 1 over infinity is also 0. This is indeterminate L'Hopital's. So now I can apply L'Hopital's rule. So remember, I still have the 2 out front. The sine of 2 over x is the cosine, the derivative is the cosine of 2 over x times negative 2 over x squared. That's the derivative of 2 over x. And the derivative of 1 over x is negative 1 over x squared. So simplifying, again I have that 2 out front and I have the limit as x approaches infinity. So I have a negative times a negative is a positive. Then I have this 2, and then these x squareds cancel. And then I have the cosine of 2 over x. So 2 times 2 is 4, and then I have the limit as x approaches infinity. And the cosine of 2 over x. Well, as x goes toward infinity, the numerator is fixed, the denominator is increasing without bounds, so this is approaching the cosine of 0, and the cosine of 0 then is going to be 1. So this is 4 times 1, which is 4. Now remember, we were using the divergence test. 4 does not equal 0, that's the criteria for the test, therefore it diverges. So the divergence test showed divergence. So we've looked at quite a few tests. We've used the integral test, we've used the P-series test, the divergence test, and we've also brought in the geometric series test again, and we've used lots of integration techniques and a lot of review topics. So, as usual, if you have any questions, please let me know. These are fun problems to work through. Make sure you have your formula sheet for Unit 3 in front of you, so that way you have all of the tests and all the criteria for the test at your fingertips. Good luck, and I hope you enjoy this assignment.